quantum computing, where I was a master's student under David Corey. During the pandemic, I was hired by Quantum Benchmark as a software engineer, where I worked on their benchmarking software. And then they got acquired by Keysight Technologies shortly before I moved on to my PhD at MIT in the quantum engineering group. So I promised that I'm an quantum engineer. So how do we engineer quantum matter? Well, we do that via quantum simulators, which were well introduced in the previous talk. But maybe I'll go through it again. Quantum simulators are essentially just easy to manipulate quantum systems with which we hope to simulate another quantum system of interest. In this near-term intermediate scale quantum era, or NISQ as it's commonly called, simulators are able to produce interesting results even when the system isn't a universal quantum computer. That is, analog systems. And there are many interesting platforms. We just heard about superconducting qubits in many different forms, as well as ion traps are pretty popular in private startups and in academia. Neutral atom arrays are starting to take the spotlight, and we're proud to have that based out of the Cambridge-Boston area. And what I'll be talking about today is nuclear magnetic resonance, which is possibly one of the oldest quantum simulation technologies, both for quantum sensing and for probing new and exciting physics. So how does an NMR simulator work? Well, if we want to talk about a time crystal, we're going to need a physical crystal. And the crystal, the solid state NMR system I'm going to be talking to you about is fluorapatite, which is very cool because it's a quasi one-dimensional nuclear spin ensemble with on-site disorder. So how do we understand this? Because this is a macroscopically sized system. Well, it's a hexagonal system with 2 fluorines per unit cell. And each of these fluorines define a chain along the crystal C axis. And they're very well separated compared to the interchain spacing. So when we align our magnetic field along the crystal's C axis, what we end up having is that a coupling within a chain is over 40 times stronger than coupling between chains. So for long times, we're able to see good one-dimensional physics. We also, in terms of our control, have this rich toolbox of flow-K engineering, or it used to be called Hamiltonian engineering techniques to control interactions. That is, we're able to take our dipolar Hamiltonian, our disordered field generated by an Ising-like coupling with the nearby phosphorus spins, and use collective control techniques to essentially sum or add and subtract Hamiltonian terms in order to change the form and strength of interactions, as well as turn it on and off disordered fields. And our interactions, the dipolar Z is essentially an Ising-like term with a flip-flop-like term that is 1 over r cubed, but in one dimension, you'll note that 1 over r cubed falls off fast enough that it's effectively nearest neighbor coupling. So additionally, our simulations happen at infinite temperature. And no, I'm not heating the system up to a plasma. Rather, we're sitting in a 300K large magnetic field at 7 Tesla. So if you look at the thermal density matrix, well, it seems like the computer's messed up some of my equations, so bear with me. What we have is essentially a Gibbs state, which the leading term in the exponential is going to be a product of the Zeeman energy splitting, h bar omega naught, and the inverse temperature beta. So if we look at this small parameter epsilon that's sitting there, it's on the order of 10 to the minus 5 or 10 to the minus 6. So our density matrix is well approximated by a large trace 1 component, an identity term, and a small density difference matrix, the magnetization. Now, if we look at the expectation value of some time evolved observable, what you see is that effectively the identity component is going to drop out because it only contributes now a traceless term in the expectation value. So what we have here is a trace of a time evolved operator and a non-time evolved operator, which is formally equal to an infinite temperature 2-point correlator now in time, which if you're doing physics research is a much more interesting object to think about. So that's what I mean by infinite temperature simulator. So now let's introduce time crystals, which are fairly abstract and kind of weird. So let's go through this a little bit closely. Time crystals are an out of equilibrium state of matter. It's kind of weird to think about. You want matter to be, within some sort of environment and stable. But the reason we say it's out of equilibrium is because it merges under repeated driving. So we're going to be repeatedly kicking this thing with energy, and the promise is that it's going to evolve and emerge into some sort of stable regime. And that stable regime breaks discrete time translation symmetry with a phenomenon known as period doubling. And since we're driving with so much energy into the system, we need to avoid the concept of flow-K heating via some many-body localization or prethermalization. That is, we need a mechanism to break ergodicity. If we're going to pump energy into the system, we need to ensure that we don't heat to infinite temperature, although we're already there, or destroy any sort of chemical potential that our system may be thermalizing to. So time crystals have been observed in the past in a few different settings. and ion traps in the Monroe group and short chains like 15 to 25, as well as superconducting qubit chips, both on Google and IBM hardware. I included both of them, so that way IBM wouldn't get mad at me. Theirs is a little bit more recent. Google's is a little bit older. There's observations in disordered dipolar ensembles in NV centers via the Lukin group as well as others, and in NMR, both in thermal and hyperpolarized ensembles, and many, many more. So this has been a very attractive field of study for many years. So what's the time crystal workflow? Well, how do we want to think of this? Well, we need to understand whether or not we have period doubling and we have interactions turned on. Obviously, if we just hit a system that's not interacting with pi pulses, you get something that looks like period doubling. So we need to ensure that we have strong interactions on and understand our mechanism for avoiding flow K heating. Now, we're in the high temperature regime, so we can immediately rule out the possibility that we're spontaneously symmetry broken as our discrete time crystalline behavior. And this makes sense because we have no appreciable ground state population, so spontaneous symmetry breaking definitely doesn't apply. That is, we need to understand the difference between many body localization, strong disordered regimes, and this pre-thermalization. And this mechanism here at the bottom was only recently proposed by Luitz et al., and it's known as pre-thermalization without temperature. It's a 2020 paper. So what's our experimental procedure? Well, we're going to repeatedly drive the system with these RY rotations centered about pi with some detuning. And we're going to allow the system to interact between rotations. And this can happen in 3 different ways. Either we can physically vary the time in which we allow the system to interact, essentially increasing the effective many-body interaction strength via just waiting longer. Or we can use Hamiltonian engineering to physically fix the flow K period and change the strength of the interactions. And additionally, we can add a quantizing field along with the dipolar interactions that commute with each other in order to try to understand the emergent U1 symmetry and how our system's pre-thermalizing. And so then if we do see period doubling, we'd like to demonstrate pre-thermalization without temperature via this theory paper and be very careful about that. And so our single flow K period unitary is this SY rotation, which is we'll call picking, and it's the discrete time translation symmetry breaking term, as well as the interactions here, which are the Z field, as well as the dipolar Z interactions, which lead to our pre-thermal Hamiltonian. So let's look at the difference between a melted and a crystallized system driving with 170-degree rotations. So there are no pi pulses here. At the first case, we see that if interactions are too weak, our magnetization response simply follows the drive, and we have what looks like a strong beating pattern that dies off within 100 microseconds. This is about the time of T2 in our system, and so this isn't too surprising. But if the interactions are increased, what we find is that period doubling emerges, and something relatively magical happens. It looks like we fully turned off interactions, even though interactions are on. We have magnetization which lasts for many milliseconds. And I think this is part of the big draw of time crystalline systems, is that by doing something that's not too clever, we're allowed to keep quantum information alive for long times. So can we construct a phase diagram? Well, if we take the Fourier transform of this magnetization response, we see that there's a 2-peak versus 1-peak structure, which is a hallmark of whether or not we're beating or period doubling. And just by taking the difference of the height of the beating peaks versus the period doubling peaks, we're able to numerically construct something that looks like a phase diagram. In blue, we have areas where our interactions and detunings conspire such that we are period doubled, so we're most likely time crystalline. And in the red area, we are beating. Our interactions weren't strong enough to move us into the many-body time crystalline state of matter. In terms of pre-thermalization, as I've been saying repeatedly, this is simply the idea that at short times, we quickly pre-thermalize to a new emergent Hamiltonian, and then we sit at that Hamiltonian for a time that's much longer than our pre-thermalization timescale. So here we've got a log linear plot showing that over many different interaction strengths, we sort of generically hit pre-thermalize within about 7 flow K periods. And then once we are pre-thermalized to that pre-thermal Hamiltonian, we now have a lifetime which is significantly longer, 30.8 flow K periods. And a flow K period here has been fixed to 120 microseconds. So this is many milliseconds of lifetime, strongly eclipsing our T2 times. Now, by turning on the Z field, we can enhance this U of 1 symmetry. And what we see is that not only does pre-thermalization can happen relatively quickly as well, but the pre-thermal timescale can be greatly enhanced, and the strength of the interactions needed to achieve strong time crystalline response is greatly minimized. So notably, when the field takes its maximum value, and because it's defined over a single flow K period, the maximum value a field can take is pi, when you take the field times the time of the flow K period, we find that the emergent prethermal lifetime is a whopping 77.5 flow K periods, which in physical units is 9.3 milliseconds, which is the best we're able to achieve in our systems. And this is going for 100 flow K kicking periods. So how do we rule out MBL? Well, in order to do that, we need to introduce this notion of disorder as a resource. And I think this is a really cool technique. And so I want to go through it a little bit slowly. So I've told you that a disordered field is generated by nearby nuclear spins, particularly phosphorus spins. And evolving under this disorder is going to let us phase tag the global state. So if we look at our chain, we see that we have these fluorine spins in blue, and each one has 3 nearby phosphorus spins, but because it's a dipolar interaction, in principle, it's interacting with all of the phosphorus spins in the crystal. And so you can imagine that if I take my magnetization and I flip it into the X plane, I now see this emergent Z field generated by the phosphorus spins. And like evolving under a gradient, I'm going to now evolve under this disordered field. And by careful phase cycling of my pulses, I can ensure that at the end of it, all I'm left with is a phase tagging along a Z magnetization direction. That is, with some clever X and Y pulses and the disordered field, we can take a local magnetization operator, SCI, and tag it with a sine of omega I, where omega I is now a random variable, and do the same exact thing with our Z magnetization observable, and tag it with an omega J, which is itself a random quantity. So what are the properties of omega I and J? Because now our global expectation value, which contains a sum over I and J, all non-local correlations, has this spatiotemporal correlation value just due to the fact that we have, well, many, many chains in our system. So we're taking essentially a statistical expectation value in a single shot. So if we go through and understand the disordered field properties with essentially just Monte Carlo, we have a series of coin flips that we can do many, many times. We can build up the disordered field distribution numerically, and you'll see that there's about 4 peak structures, and we understand that because there's 3 nearby phosphorus spins, and so you have an emergent sort of 3-half structure that dominates. But overall, a single Gaussian fit has seemed to work fairly well. And in order to characterize this experimentally, it behooves us to tilt the disordered field along a 45-degree axis in the X plus Z plane. That is, we have a tilted disorder by using flow K engineering. So this does 2 things for us. We can extract the disorder strength via the experiments, as well as calibrate our ability to control the disordered field using our pulses and Hamiltonian engineering techniques. Essentially, we should just see a Gaussian with an asymptote. And if we do this in the lab without being too clever, what we find is that the X and the Z quadrature measurements do not agree. So we took some time and understood that our pulses were short. We had some Hamiltonian drift. We had some phase transients. And so we improved our fidelities by essentially going through and adding in a frame change technique, which is another paper that recently came out in the Journal of Magnetic Resonance, if you're interested. But so this is just to say that we are able to calibrate and compute the disordered field and control it very well and extract the value and compare it to numerics. So now that we understand how the disordered field works, let's think about it for a second. Each phosphorus spin is essentially 50-50 up-down with the thermal populations. So the disordered field is effectively uncorrelated at long distances just by a 1/r³ interaction. But short correlations might exist. However, we think that they can be suppressed by evolving longer. Imagine this at very short times, the sine of omega IT, the 2 field windings are effectively on top of each other. So they're strongly correlated. But if we just evolve for slightly longer times, the clock hands move slightly out of sync. And what you end up getting is that they're effectively going to die off. And so our expectation value here, the sine of omega I and sine of omega J, go to a Kronecker delta function. So that's really awesome, because now we've taken a global expectation value, written it as the sum of local expectation values, and with a little bit of translational invariance, we now have a single site autocorrelation, which is really cool. So how do we use this to rule out many-body localization? Well, the idea is if we were many-body localized, then the local magnetization should oscillate between overlapping local intervals of motion. We should have emergent eigenstates that are very well localized. And so by looking at the difference between this global expectation value, which contains long-range correlations, and the local expectation value, which contains no long-range correlations, we should be able to determine whether our prethermal state is dominated by non-local correlations. And the experimental data shows pretty starkly that the local Z magnetization decays almost instantly, whereas the global Z magnetization stays around for a long time when we're in a time crystalline regime. And now we compare this to the numerical predictions of the Luitz et al. Theory paper. They predict the same exact thing. And we're able to measure that. And this is a really huge change in sort of the regime of NMR, where we've been able to consider 10 to the 23 spins, but we've never been able to look at a single spin before without, say, an NV center or a laser or doing something very clever. Now we can, and it's really cool. I think one of my favorite moments was when a referee called this the theorist's dream initial state, which I think we should start using more because it's really exciting. So let me finish up and conclude now. What have we done here today? Well, we've experimentally demonstrated the existence of time crystals at infinite temperature. We're not the first to do this, but we're the second, but we've been a little bit more careful in our phase diagram construction. However, we've also experimentally demonstrated and verified prethermalization without temperature, and this was enabled by using local observables to conclusively rule out MBL as proposed by this Luitz et al. Theory paper, which is great. So what's next for our group? Well, what we're doing is trying to understand a sample with disorder and 3D connectivity in order to apply this disordered state technique to more interesting systems. Avoid the curse of one-dimensionality where everything is integrable and theorists are able to answer the questions before the experimentalists can get there. Then once we have that system, we want to perform transport experiments, namely try to directly measure spin diffusion without doing any crazy fast gradient switching, and understand what happens to spin diffusion and transport in general in the presence of strong disorder. And so I'm happy to say that this characterization of disordered sample is done. You can see it here on the right. Our diffusion measurements are in progress as we speak. And we're working with theorists and as well, we've got a great team that are trying to understand the theory behind here in the case where numerics don't really help very much. So with that, thank you all very much.